Okay, and this is just essentially called reactions in solutions. And it uses, again, solubility, and we're also going to need our activity series. So you're going to want your data sheet from your periodic table. And essentially, if I'm to just distill this down to the simplest, what we're doing here today, we are going to look back at double displacement reactions and single displacement reactions, and we're going to look at them now in greater detail on an ion by ion basis so that we can understand what's happening in those reactions in a truer sense. In the past, we look at double displacement reactions and single displacement reactions, and we just trade the partners, right? We think of a snowball dance, or can I cut in, all that type of thing. And we've kind of expanded it this year where you've talked about, does the cut-in take place, the activity series, or is there a solid formed, our solubility chart to determine whether it's a solid or not. And that's good, that's more detail, but now we want to look at it in greater detail. Each ion, what's each ion doing, all right? What is its job in the chemical reaction? So, just a little bit of a review, all right? And you can write this down. In the end, the process that we're completing is something called a net ionic equation. It is essentially a chemical reaction that is looking at ions instead of compounds. And before we get into doing examples, I just want you to recall what dissociation means. And how we use our solubility chart to determine if it will dissociate. So I'm linking two skills that you already have, and I'm bringing them together. My example is sodium chloride. Now, at the beginning of this unit, right before we had our discussion on polar and nonpolar, we talked about ions and how when they get into water, if they dissolve, they dissociate from each other. That's it. You go your way, I'll go my way. It was nice hanging out with you in the crystal lattice structure, but now that we're dissolved in water, I don't need you anymore. Thanks for coming out. We'll see you later. Dissociate. All right? In the past, when we looked at double displacement reaction, I asked you to identify whether something would be solid or aqueous, and we used our solubility chart. Now let's put those two things together. If you're given sodium chloride and you're not sure whether it's aqueous or not, you'll find it on the chart, sodium and chloride, and because it's a sodium, we know it's going to be aqueous. I'm not going to sing the song again, but sodium is one of those guys that are always aqueous. So if we see that it's aqueous, we now know that it will dissociate, and so we now can take it to the next step. If this is aqueous, we can say this is going to become Na+, aqueous, and Cl-, aqueous. So in the past, when you saw AQ, you just said, oh, it will dissolve. It will disappear into the water, right? That's what aqueous meant to you guys. Now I need you to think a little harder, a little further. If you see aqueous, yes, it disappears into the water, but we now know that it breaks apart into its sodium ions and its chloride ions, and they're floating around in the water. All right? Okay. And again, just to practice, another example of an aqueous one. Again, if you're given FeNO3, we check the chart. we find that it's aqueous, also it's a nitrate. Remember, nitrate was one of those ones that are all aqueous. What are the others that are always aqueous? Sodium, what's that? Ammonium, very good. Yeah. Potassium. You have any of those in any structure, you don't even need to check the chart, aqueous. So I guess the structure of this is to remind us how to dissociate it. We did this at the beginning of this particular unit. I'm going to have one Fe. What's the charge on that Fe going to be in this particular situation? Reversing crossover, or we're checking to see which one it is. Yep. Yeah, it's an iron 2. So this is iron with a +2 charge. And this little 2 means that there's 2 nitrates, and the 2 are going to separate. So the little 2 becomes the coefficient. I end up with 2 nitrates, NO3 minus, and again, it's also aqueous. So again, I'm linking what we've learned in the past, how to determine whether it's solid or aqueous, but now if it is aqueous, we can break it into its individual ions. Okay? And if it is insoluble or slightly soluble, in the case of our particular chart, if it comes up as an S, then we say it does not dissociate. So if we were to get silver chloride, check out the silver, cross-reference it with the chloride. And I guess if we were to ask you to dissociate that, well, nothing would happen. It doesn't dissociate. You could write no reaction, but actually in the examples that we do, you just simply rewrite it unchanged. It didn't do anything. It doesn't fall apart into its ions. It stays together in that crystal structure. And again, we use our solubility chart in order to determine this. Okay, so now that we have recalled how to determine whether it's aqueous, and also recalled that if it is aqueous, it breaks apart with its ions, we're ready to now look at something like double displacement on an ion by ion basis instead of just trading partners. Okay, so consider the following reaction. Yeah, you can just call it example 1 if you'd like. It's the first of a bunch of examples we're going to do. Yep. So I present this to you as simply a double displacement reaction. We have sodium chloride in one solution. We have silver nitrate in another solution. We bring them together, and we wonder whether we're going to get a precipitate or not. In doing these questions, always start with the regular balanced chemical equation, just like we would if we were doing a regular double displacement reaction. So go ahead and trade the partners, cross over to get the proper formulas, balance, and use your solubility chart to determine whether you get a solid or whether it is aqueous. So this is review of double displacement reactions. And this is something you can do. Again, swap partners, make sure you use the crossover, make sure everything's looking good, check your chart, and once you have some of that information, I'll take it. Yeah, Atlee, what do you got? NaNO3, and what is that? Aqueous, and what else? Sorry? AgCl, and I think that's 1 and 1 as well, right? And what is this? Solid. You'll notice we use the exact same kind of compounds we used in our examples. That was on purpose. And this is nice because it's all 1, 1, 1, 1, 1. Everybody's 1, so when we cross it over, it's good. This is the balanced chemical equation. Please write that off to the side. Because I'm going to this is the beginning of a 3-step process to get a good analysis on what's happening in the chemical reaction. So the next thing we do is we complete something called the total ionic equation. I'll define that in a moment. The total ionic equation, TI. And what we do when we go from the balanced chemical equation to the total ionic equation is for every compound that is aqueous, we dissociate them, just like we did in the last little equation. And for every chemical that is solid, we do nothing to it because it doesn't dissociate. So I look at the sodium chloride and I do exactly what I did on the last slide. I know that it is Na plus aqueous and a Cl minus aqueous. So I simply separate it into its ions. And I'll do the same with the silver nitrate because it's also aqueous. Ag plus aqueous plus NO3 minus aqueous. And I will do the same with the sodium nitrate because it's also aqueous. Na plus aqueous plus NO3 minus aqueous. Now, AgCl is a solid. They didn't dissociate. They stick together upon trading. So I just rewrite it exactly the same way. AgCl solid. So that's the total ionic equation because it contains all of the ions that are existing in the solution. So now we can take a little closer look at what's happening in a double displacement reaction in an actual solution at a nice close view here. So what happens? We've got Na and Cl and they're kind of in the water, and we've got Ag and NO3 and they're kind of in the water. Then you mix them together and the Na might bump up against an NO3, but they're always aqueous, so they don't actually dance. If we're thinking about them trading partners, it's like the sodium goes, I'm not interested in you. Sorry, nitrate. Thanks, but no thanks. An unsuccessful reaction. And the Ag and the Cl get together and they stick together and then we get a solid. You'll notice that there are some ions that exist on both sides of the equation that are exactly the same. Tell me an ion that exists on both sides of that chemical equation that are really exactly the same. Yep. Na plus. What else? Yep. No, the chloride isn't the same. This chloride is aqueous and is in solution. This chloride is stuck together with a silver and is in a solid. Those are different types of chlorides. Yep. The nitrate. These two ions, the sodium and the nitrate, are not actually participating in the chemical reaction. They're really just there. They're not producing a new solid, they're not producing a new gas, they're not doing anything. We call these ions that are the same on both sides spectators. They're spectator ions. They're not participating in the chemical reaction. And when we want to get what is called the net ionic equation, now the net ionic equation gets rid of the fluff, gets rid of the spectators. They're not participating in the chemical reaction anyway, so let's just get rid of them, and that's what we do to go from the total ionic to the net ionic. We cancel out the spectator ions, that guy and that guy, and they've got to be the same number and type. In a moment, we'll have a more complicated one that has some coefficients in there. They've got to have the same amount, and they've got to be the same type. Nitrate, nitrate. Once we've canceled them away, we can rewrite the equation without the spectators. A Cl minus aqueous gets together with an Ag plus aqueous, and that results in an AgCl solid. All right? And that's the net ionic equation. That's what's actually taking place in the reaction. So we've got a double displacement reaction that at one point in your careers you believed to be some kind of nice, fair snowball dance. Everyone trade new partners to dance with. And now I told you, okay, but one of them's going to be a solid. Oh, that's fun. So they can trade and somebody might get to be a solid, but the other ones will stay aqueous. And when we really look at this, it's not nearly as exciting. Sodium, what does sodium do? Sodium goes to the dance with chloride, right? Chloride says, sodium, want to go to the dance? Yeah, I'd love to go to the dance. As soon as it's dissolved in water, chloride goes, hey, thanks for the ride in the dance, buddy. That was pretty good. I'll see you later. I'm out of here. So then right away, sodium gets dumped, and chloride takes off. And what happens in the end? Sodium stands there on the sidelines. I just want someone to dance with. Where in the end, sodium really doesn't dance with anyone. Hence, it's called a spectator ion. All right? Nitrate's the same thing. Nitrate is also just the chump that brings silver to the dance. So sodium and nitrate, because they're always aqueous, they never get to dance. As soon as you put them in the water, they separate out, and they will never participate in a reaction that will result in a precipitate. All right? They'll never participate. So sodium, because they're all AQs along there, always a spectator. Always, always, always. Same with nitrate, and same with ammonium, and same with potassium. They will never, ever, in a double displacement reaction, be in the net ionic equation. They go to the dance, and then they're dumped, and then no reaction. Nothing happens. Poor thing. Anyway, okay. So that's more of exactly what's happening in an actual double displacement. So in this case, we had a chloride get together with a silver. A couple of definitions here, or a definition on what a spectator ion is. Now that's not to say that sodium, potassium, and ammonium and nitrate are the only spectator ions. You could have something like a chloride that sometimes doesn't react with something on the side. Chloride could be a spectator ion. Every time chloride, if you look on your chart, has AQs on it, then if it comes together with those, it'll be a spectator. Silver is one of the few things that'll actually precipitate a chloride out. Okay, so now we're just going to essentially go through a few more examples of double displacement so we can practice breaking them apart, and then we'll take a look at what happens in a single displacement. Again, it's not as straight up as someone cutting into a dance. So, potassium iodide and lead 2 nitrate. I guess the first example was a double displacement example, but it was also just an example on how we have spectators and how we break things into ions. I'm also being a little meaner here on this one in that you've got to come up with the formulas for the reactants. You got to check to see if they're aqueous or not, and then we got to trade them, and then we've got to see whether they're aqueous. We got to balance it up. The first thing we got to do is that balanced chemical equation, BCE. Now, as you're coming up with some formulas, I want to stress to you, this process has nothing to do with stoichiometry. We never use a net ionic equation to solve a stoichiometry problem. Stoichiometry is all about ratios, and all we need is a balanced chemical equation to do a stoichiometry problem. This is about looking deeper into the chemical reaction. So when we start doing stoichiometry again tomorrow, we're not going to be doing these things. We're just needing the balanced chemical equation and going from there. Again, if you're unsure, pencil is the best way to go with this stuff. Somebody have some formulas? I don't need a balanced chemical equation necessarily, just to get me started here. Yeah, what do you got, Brent? KI. Do you know whether it's a aqueous or not, or have you checked that? Yep. Oops, look at, and I can't erase. This is going to be a mess now. PbNO3 brackets 2, and what is it? Aqueous. Okay, what do you, okay, 2 something, 2? 2KNO3, and what's it? Yep, they're all aqueous, yep. PBI2. I hope not. That wouldn't be fun. It's a solid. If it was all aqueous, then that would be the boringest dance in the history of dances. Okay. I suppose you could have it all aqueous. Like if you had potassium nitrate and sodium chloride, you'd have all AQs. That wouldn't be much of a dance. It'd be like, like that grade 8 dance. There would be no net ionic equation. Everything would cancel out. It means nothing happened, right? Okay, let's keep going with this one. The total ionic equation. Now, because I have 2 Ki formula units, 2K plus aqueous plus 2I minus aqueous. So those 2 that are in the coefficient becomes the coefficients of that one. Now, in this case, there's a 2 behind the nitrate. And as we know, that means I'm going to have 2 nitrates. So in this case, I'm going to have a Pb plus 2 aqueous and 2NO3 minus aqueous. So in this example, I'm illustrating to you that coefficients can come from coefficients in the total ionic equation, or this 2 in front of the nitrate, its coefficient can come from that subscript 2, because that means there's 2 nitrates. Yep. Then you'd have 4, because you'd have 2 times 2. Yeah. The question essentially was, what if we had 2 PbNO3, right? Then you'd have 2 leads and 4 nitrates, because you'd multiply the little 2 with the big 2. Okay? Again, this is aqueous, and there's 2 of them. 2K plus aqueous. 2NO3 minus aqueous. And you'll notice I'm running out of room, so I'm going to just put a plus and I'll write it underneath. PBI2 solid. We do nothing if it is solid. Spectators. What are the spectator ions in here? Same on both sides. Yep. Yep, there's 2 potassium. They're not doing anything exciting. Anything else? 2 nitrates. Excellent. There it is there. And once you've canceled out the spectator ions, all you have to do is rewrite to get the net. Right? And you got that? Yep. Excellent. So in this case, we had 2 iodide ions coming together with a lead-2 ion to make the precipitate lead-2 iodide. All right? Okay. Hold on one second. No, I want to jump ahead. Yep, we'll do that one. We're jumping to C. The last example that I missed is really another example just like the one we did before, nothing special. But because I talked about polarity, I want to make sure everything we get done, so it's not a big deal. We missed. Now this one is a little special. sulfuric acid and sodium hydroxide. What do we call this type of reaction? Yeah, it's a neutralization, and we did neutralizations when we looked at double displacement reactions, so we need to look at it here as well. Do we have a formula for sulfuric acid? Oh, yep. Oh, excellent. H2SO4. H2SO4, and it is aqueous because it's an acid, right? Remember, acids are aqueous. When we put them in the water, they do fall apart. And sodium hydroxide, pretty straightforward, NaOH, and that is aqueous as well. Again, it's an ionic with a sodium, so it's going to be aqueous. And what are our products for this, Chelsea? H2O and Na, you said Na2SO4, I assume. And what state is the H2O in? Yeah, it's a liquid. It's not aqueous, it's a liquid. Which means it's not ions. It's not going to be aqueous. It's just a liquid itself. Yep. Yes, you do, because it's different than the other side. So yes, you treat it exactly as the solid. And this guy is aqueous. And we don't have this balanced yet. Does somebody, where are my coefficients going? Which one? Yep. 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 And so, again, total ionic equation. Anything that says aqueous, we break apart. Anything that is not aqueous, like liquid or solid, we don't break it apart. Now, this guy here, 2 H pluses, comes off of that thing. We treat it, the H, just like a K or an Na. The liquid stays together. It's just like a solid, but it's in the liquid state. It means that it doesn't fall apart. Oh, I'm so running out of room. 2 Na plus aqueous and an SO4, and that's 2 minus aqueous. Spectators. Things that are exactly the same on both sides. No? Oh, what's the question?
Which one's solid?
There isn't in this case. In this case, it's a liquid, but it means that it's formed a molecule that isn't going to fall apart. So we treat it like a solid. We just leave it the same. Right? It doesn't fall apart. It doesn't turn into ions. So what do we have for spectators? Yep. Yep, we got sulfate on both sides. And what else? Yep, we've got 2 sodiums. Again, if you do it right, the numbers of sodiums should also be the same. If you make a mistake and you've got like 1 sodium on one side and 2 sodiums on the other side, you've made a mistake somewhere. You've got to kind of go back and figure that out. H plus aqueous, OH aqueous, H2O liquid, those are different things. We write that down. Net ionic equation, 2H plus aqueous plus 2OH minus aqueous to produce 2H2O liquid. All right? This, with some different numbers of H's and OH's, is always the net ionic equation for a neutralization reaction. It's always a certain amount of H pluses coming together with a certain amount of OH's to always produce water. That is the net ionic equation for all neutralization reactions. Okay? Depending on the type of acid and how many H's they have and the type of base, that's going to change the numbers in front, but they're always going to be a certain number of H's with a certain number of OH's to produce water. Yep.
Another, you want sodium,
Yeah?
shouldn't there be a coefficient?
No, because this 2 came from the fact that there were 2 sodiums, not from the fact that there were 2 sodium hydroxides. There's a big difference. These 2's come from this 2, which means I've got 2 sodium hydroxide, and that breaks apart into 2 sodiums and 2 hydroxides. This 2 comes from the fact that there are 2 sodiums in each sodium sulfate. So when the sodiums fall off, you're going to get 2 of them, and that leaves 1 sulfate that the 2 sodiums fell off of. They come from 2 different places. I could say it again, but I would use the exact same words that I just spoke.
I thought there was a +2 charge on the SO4.
There's a -2 charge on the SO4, and it's right there. What would you like to do with that -2 charge? I don't put charges as coefficients. I put the number of things as coefficients. It doesn't come from the charge. I'm going to put the next example up, and then I need to have a sit-down discussion with you on how we just can't take numbers and put them in different places, that the numbers have to come from actual important spots. Because you just want to take numbers and put them in different places, and they don't do that. They have to come from actual important spots and then go into those places. So let's look at some single displacement situations. So I'm not going to go over the review of how the activity series works, because we're going to use that here in a moment. So again, just like before, you can write down the zinc. And by the way, the zinc is in the solid state, because all these gray guys are solids and the red guys are gases. But they're in their elemental states. If we were to use bromine or mercury, they would be liquids. And copper 2 sulfate is a compound, and in order to do this reaction, we will need it to be dissolved in water. It will be aqueous, unless it states otherwise on the solubility chart. Copper is 2, or that's the it says 2, yeah, copper is 2, it says it right there. Sulfate is 2, so 2 and 2, right? And that has to be an aqueous solution. We have to have that dissolved. We're putting a hunk of copper in a solution of copper 2 sulfate. Now we check our activity series. Anybody remember how that works? How do we determine that? Yep. Yeah, the ones at the bottom want to be by themselves. Right? Gold's at the bottom. Gold will displace so that it can be by itself. So we check for zinc and we check for copper, and we see that, which one's on the bottom? Copper, is it by itself? No, so the trade's going to happen here. It wouldn't be a very good example if it didn't happen and we had no reaction and we had to stop. It wouldn't be any fun. So we are going to have a reaction, copper. And when that copper switches, I don't remember if you remember when I put the silver in there, we actually get silver out of it. We get silver metal. So in this case, we will get solid copper. So when something displaces out, you will get that element in its elemental state as dictated by the periodic table. And copper is gray, it is a solid. The zinc will swap out, and it will become zinc sulfate, SO4, and what's the oxidation state of zinc? 2, so it's a nice trade. And really we should check to see whether zinc sulfate is aqueous or not on our solubility chart, because in theory, we could have a double displacement with a solid being formed at the end. So what is zinc sulfate from our solubility chart? Is it aqueous? So it is aqueous. Excellent. And because there are twos, all these twos for the oxidation states, I think that's balanced, isn't it? Let's now do the total ionic equation. Now, the total ionic equation breaks things into their ions and indicates what charge they have when they're dissolved in solution. Now, you'll know that the zinc, you'll see there that it's a solid. It's not in solution. But for the sake of making your lives a little easier, I'm going to include the charge that's on this elemental zinc. So I'm going to have zinc solid, and I now need the charge on a zinc atom. Now, this is something that is really quite easy, but I need to force your brains to think about it. If there is a zinc atom, just an atom, in a piece of metal, it hasn't reacted to become aqueous, it hasn't reacted to form an ion, it hasn't gained or lost any electrons, it's just an atom. What's the charge on that atom? Yep, there's no charge on it because it's got the same number of protons as it does electrons. So the charge on atoms that are in their elemental state, solid, even if they were liquid, they would still be atoms. The charge is 0. I'm going to put a little 0 up here. The oxidation state of an atom is 0. It hasn't gained or lost any electrons. Let's continue with the aqueous. Copper, this has been reacted. If I do the reverse crossover, it's copper plus 2 aqueous, and it is SO4 minus 2 aqueous, just like we did above, right? If it's aqueous, they're going to break apart into their ions. Now I've got copper, and this copper has become a solid. It is back into its elemental state. It is an atom. What's the charge on that copper? 0. Cu, oh, what a mess, solid, 0. I got to fix the eraser on this thing so I don't have to scribble everything. Perfect. Let's keep going. Zinc is now in with the sulfate, which means it had to become an ion at some point in time. Reverse crossover, Zn plus 2 aqueous, and SO4 minus 2 aqueous, and there's some scribbles in there. The plus is pretty small, but I think we can see it. The key to doing single displacement reactions is to realize that when we've got the atoms in their elemental state, their charge is 0. And when we've got them in an ionic compound, their charge is whatever the ionic compound dictates. Spectator ions. Do we have any spectators in here? Things that are exactly the same on the left and the right. Yep, Brody? The sulfate is a spectator in this case. The sulfate did not do anything in this reaction except to bring the copper ions into the solution. This is going to change our view on what a single displacement reaction is quite greatly, because up to this point we thought of a single displacement reaction as being someone who just cuts into the dance, displaces it. Let's write the net ionic equation. Net ionic equation. I'm writing everything down that is not the spectator. Zinc 0, solid, Cu plus 2, aqueous, Cu, solid, 0, Zn plus 2, aqueous. The sulfate has nothing to do with it. The other dance partner has nothing to do with it. Let's think carefully about what exactly happened here. Zinc, which had a charge of 0, was just standing there behaving like a regular atom, encounters a copper which has a charge of plus 2. After their interaction, copper now has a charge of 0 and zinc has a charge of plus 2. What took place between the zinc and the copper? Yep. The zinc gave the copper 2 electrons. That's what happens in all single displacement reactions. A single displacement reaction comes down to one of the reactants giving some electrons to another reactant to then turn it into a solid, and it then becomes an ion. So we have zinc giving 2 electrons to copper. Copper says, thank you very much, and goes on its way. It has nothing to do with cutting in at a dance. This is a drug deal going on right here. That's what this is. Single displacement reactions are shady, right? Sulfate's driving the car, drops copper off so that it could pick up a couple of electrons, and away it goes. Sheepers. Crazy things. All right, okay, that's silliness. But that's down to exactly what's actually happening in a single displacement reaction. It's a transfer of electrons from the solid to the ion, where it then becomes atomic again, and then the other one becomes ionic. Okay. Oh yeah, that's good. And let's do, I think, one more example. I think this might be my last example. Formula for hydrochloric acid? HCl. Now, I'm not putting the charges in until I get to my total ionic equation, right? So I'm not worried. I'm treating this like, just like we treat any single displacement. In this case, we've got hydrogen, and which one's below, magnesium or hydrogen? Yeah, because it wouldn't be a very good example. Again, it would come to an end and we wouldn't have anything. What do I have to write for the hydrogen as the product? Yeah, H2, very good. H2 gas plus, and then I'm going to have MgCl, and it's going to cross over for a 2. And again, we should check to see if this is aqueous or not, because if it isn't aqueous, then I've got a double displacement and a solid being formed, and then it becomes interesting. You could have that happen. Is this aqueous? Yeah, so aqueous. You could, in theory, have that happen. It would mean the total ionic equation, you'd just break the HCl apart, right? And then there'd be nothing to cancel out. Your net ionic equation would be the same if I had a solid in here. There'd be no aqueous points on this part. Okay, so total ionic equation, Mg solid, what's the charge on it? 0, excellent. And then, oh, it's not balanced yet, is it? Because I think I need a 2 here, don't I? Because I'm going to need 2 of these H pluses, aqueous, and 2 of the Cl minus, aqueous. H2 gas. It also, charge of 0. In H2, they share perfectly. So no atom has more control over that shared electron than the other. So it's like they really have 1 electron still. It's perfect sharing. Mg plus 2 plus 2Cl minus, oh, sorry, and they're both AQs. Spectator, oh, yeah, question? Yeah, yes, it is. It's H2. It's molecular. It's like the water coming together to form a liquid molecule. They come together to form a gaseous molecule. They do not fall apart. They're not two H's, they're H2. It's only if they're aqueous do you break them apart. Spectators, yep. Yeah, the chlorides. Rewrite, and you've got it. Net ionic equation, Mg0 solid, 2H plus, H20 gas, and Mg plus 2. And again, the Mg is pushing its electrons onto those two little hydrogens. It's just mean, tell you. All right, so those are net ionic equations for single displacement. It's an electron transfer. It's about trading electrons in a reaction like that. That's great. There are some practice problems. Page 355. I want to look at these questions for a minute. I'm going to stop the recorder, though, here as you guys are writing. I've got an extra worksheet that